We've talked previously about adding up areas under the curve. We have some height function f, and we're taking little steps across some horizontal axis, which could be called x, from some initial x to some final x. We can visualize that as the vertical axis f, adding up little steps across our motion in x. We cut into little slices, and we're performing a summation. This says the height value, f, whatever it might be, multiplied by little steps in the width, little steps dx in the width. That gives us a little sliver of area, and we add up the slivers from our initial position to our final position. And as we accumulate the area across in each one of those slices, the total area under the curve is written in this form as the summation of heights times little steps in widths from some starting position, x initial, to some final position, x final. So this is, in English, the area under the f versus x plot from x initial to x final. That's the English representation of that equation for an integration. What we want to do now is to lay the groundwork for how one actually performs these integrations, and also connect the idea of area under the curve to slope taking. What we saw previously was that slope taking allowed us to go from position to velocity to acceleration, and area under the curve allowed us to go from acceleration to velocity to position. So these things seem in some way to be sort of inverses of each other. Slope taking takes us down the ladder. Area accumulating takes us back up the ladder. They seem to be undoing each other and allowing us to ascend and descend between relationships that are similar to the position, velocity, acceleration, ladder relationships. But let's be specific now. Let's be specific now about the way that works. Let's imagine that our function f, which was the height function of the graph we're looking at, was in fact the slope function for some other function, which we'll write capital F. Now we're not going to be specific at the moment about either of those functions. We just say we have some function f whose height is accumulating some area under the curve, and we happen to know that that function f is the rate of change of some other function, capital F. If that were the case, watch what happens here. This integration, which we're trying to compute, is the accumulated area of the height function times the width function from the initial x to the final x. But if that height function f is itself the slope of some other function, we can rewrite it as rate of change of capital F with respect to x times rate of change of x, or small step in x. The small steps simply cancel each other, and this becomes the accumulation of the small steps in f. From where and to? From f corresponding to the initial x to f corresponding to the final x. But this we can evaluate trivially. We know the answer. Accumulating all the small steps in something gives us the big change in that same thing. So the accumulated changes add up all the small changes in capital F, whatever it is. You add up all the small changes in F, what do you get? The big change in F. F at the final x minus F at the initial x. In other words, the big change or the finite change in F. This is really, really powerful. Let's not overlook the result, and let's summarize. Given some integration, a height function times a width interval, height function times a width interval. Given some integration, added up, height function times width interval from initial value to final value. The answer is, the result of that integration is the change delta in the function. Whose derivative is your integrand. This is called the differential, dx. The thing inside the integration that sits in front of the differential, the height function, f, is called the integrand. Sometimes the integrand can just be 1. If you don't see anything, the integrand's 1. The integration of some integrand times a width interval. How do you calculate it? The answer is you have to guess or otherwise figure out the function whose derivative is your integrand. Find how that function changes, and that's the result of your original sum. That's the method. Whatever your integrand is, by hook or crook, find the thing whose derivative is that. Find the thing whose slope gives you the integrand. Then find how that higher level function changes from initial to final, and that's the result of your integration. In fact, we saw an example of that before in the context of position, velocity, acceleration. We saw that change in velocity is the area under the acceleration versus time graph from time 0 to final time. In other words, change in velocity is the integration of the height function acceleration times steps in time. In principle, how would we do this integration? The integrand is a. The result has got to be the change in the thing whose derivative is a. Well, the derivative of what is a? V. What's the result? Change in v. Correspondingly, if we integrate velocity times changes in time, the area under the velocity versus time graph, we know what it is, but let's use this approach. The integrand is velocity. What's the function whose derivative is velocity? Position. And the result, of course, is the change in the position. It fits in consistently with the new framework.